Good afternoon, everyone. This is the last session of the day. The first paper is OpenMIND, Planning and Adapting in Domains with Novelty by David Musliner, Michael Pelican, Matthew McClure, Stephen Johnson, Rick Friedman, and Cory Knudson, all from SIFT. And David, please take it over.
Thank you, Hector. I also want to point out that this work has been the result of a tremendous amount of collaboration with folks at University of Texas in Dallas, Australian National University, Washington State University, and NRL. So there has been a lot of collaboration to make this work, and I think you'll see how it all plays together in a moment. Quick outline, we'll talk about the Salon program, a Darpa program that this work was funded by, just to give you a background on what we're aiming at, what are we trying to do. We'll talk about what is novelty in the context of that program, and you'll see why that's important. We'll talk about what is novel in our research, and we'll talk about the evaluation approach, which is part of the novel research across the program. We'll give you a quick glimpse of results so far, and if we have time, we'll talk about some insights and lessons. So the Darpa Salon program is a big program, hard to describe quickly. It stands for Science of Artificial Intelligence and Learning for Open World Novelty. And the objective is to build domain-independent, competent agents that can adapt to novelty in their environment. Now, what do we mean by competent? Well, it can be an agent that is either pre-trained or has been manually engineered or learned offline in another way to be capable of accomplishing one or more tasks in an expected environment. I'll give you some examples in a moment. And different performers in the program are looking at different kinds of agents and different kinds of tasks. But the main idea here is that you're not starting from scratch necessarily every time when you wake up in the world. So it's not pure RL from scratch necessarily. And in fact, our agent that we're building, OpenMIND, is a planning and plan execution agent in a very typical sense, as you'll see later. So new goals in that sense are very commonly considered by planning and plan execution agents. But in the Salon program, new goals are not the novelties. The novelties are in the domain, and I'll give you some examples here. On the left, you see Polycraft, which is a Minecraft modification that is the first domain we started working on. And OpenMIND plays this game by running around in the environment, breaking up trees into logs and building pogo sticks. It has to build one pogo stick per game. It wins the game if it builds the pogo stick, and it gets a score based on how hard it had to work to build the pogo stick, how many trees it broke, and so on and so forth. And novelties might occur in Polycraft, just for example, if a axe appears in the domain. And the agent might learn after trying out the axe on various things that an axe is a very good way to break a tree. It costs less than breaking it other ways. And as a result, it gets better score. So maybe it should keep using the axe in future games. On the middle chart is a picture of Science Birds, which is a sort of Angry Birds modification. In this game, you're flinging angry birds at pigs across the screen, and the objective is to kill all the pigs. Novelties might occur, of course, when pigs fly, for example. And on the right is Vizdoom, which is a sort of two-dimensional first-person shooter game that the agent has to run around, killing all the enemies and picking up health packs and ammo packs. And a novelty might be, for example, that an ammo pack isn't an ammo pack, it's a health pack, or vice versa. So SIFT's OpenMIND agent has been playing the Polycraft game the longest. We started in that and worked on it for 6 months, and then we started in Science Birds, and most recently we were starting in Vizdoom. So I have some preliminary results for the first two, but not the third one. We haven't been evaluated in the third one yet. So one of the reviewers asked for our formal definition of novelty. If you read the paper, you'll find no Greek and no formality. But to paraphrase the Supreme Court, one version of novelty that fits this program's concept of novelty is that I know it when I see it because I haven't seen it before. So an agent knows novelty because it's something it hasn't seen before. And a better way to think about it is really to read Pat Langley's AAAI 20 paper, where he talks about novelty as being detectable, sudden, and persistent changes to the agent's environment. So I gave you some examples of those, like the appearance of the axe. And some novelties can be opportunities. So the axe appearing is an opportunity to learn that axes are better at breaking trees and you should use them. Some novelties may be impediments. So it turns out that one of the novelties that we know can happen in Polycraft, a game where we're making pogo sticks, is that blocks that are called fence blocks can appear surrounding the trees. They prevent the agent from reaching the trees, so they're blocking the ability of the agent to accomplish its task in the normal way. And some novelties can be irrelevant, like there might be butterflies flying around in science birds, and if they don't block the birds flying across the screen, they just distract you, then they're irrelevant. And I should point out that although I showed pictures of each of these domains, our agent plays them using a symbolic interface. So we get symbols, JSON essentially, that tells us where the trees are in Polycraft and what tools we have and things like that. And we speak to the games using symbolic actions that can be parameterized, like put the axe in your hand and use it to hit a tree. Now, across the whole Salon program, there's a concept of evaluation and the effect of novelty that looks roughly like this graph. On the bottom axis would be a series of games played over time that constitute one trial. And the overall evaluation will be a whole bunch of trials. And at the beginning of each trial, your agent wakes up anew. Can't retain information across trials, but between the games within a trial, that's where it's supposed to be learning. And on the vertical axis is some kind of task performance metric, and it's different for each of the different games. In Polycraft, it's basically you get a whole bunch of points for making the pogo stick, and then you remove the cost that you spent breaking up trees and things. So the general idea here is that as you play the series of games, there might be a pre-training activity that where the agent's performance asymptotes, and then it plays for a while. And then what we call the red button is pushed. Novelty is suddenly introduced into the world, and the agent is not told that. It just may get different percepts or behaviors of how it works with the world might change. And the agent's performance may be reduced as a result, particularly, for example, with fence blocks surround all the trees, and it's never seen fence blocks before. Just walking towards the trees normally won't work. And it's going to have to figure out something to do. And so that's there's a pre-novelty period of time that you're playing normal games, and then the novelty occurs. You're not told about it. You have to try and detect it and respond to it. And if you look at the light gray line, the people who are making the simulations are supposed to provide a baseline agent that can play the game, possibly even better than our agent can, because it's highly tuned to the particular domain. But when the novelty occurs, that baseline agent is not intended to detect or adapt. And so it may decrease its performance significantly. And our agent, the black line, is intended to detect and adapt and improve its performance, potentially exceeding its pre-novelty performance. Now, that's going to vary a lot depending on what kind of novelty it is. But there'll be formal metrics to assess the detection and performance adaptation based on this kind of chart. And I'll talk about those in a little bit. But just to give you an idea of what that looks like from the perspective of OpenMIND, here are two charts showing over time. And so the bottom axis is the game number, how the score changes as the agent plays through two different trials. On the left is the first trial where you wake up with an axe in inventory, like I mentioned. And that novelty occurs, the so-called red button push occurs at game 6. That's why I've got this little box of yellow around there. And so you see the agent is playing along, it's earning a certain score, it gets the axe and luckily tries the axe on a tree, finds out that gives it a much better score by lowering the cost of breaking up trees. And for the rest of the trial, as long as it gets axes in inventory, it's going to keep using them and each game and get better scores. So it learns essentially if you have an axe, use it. And on the second plot here, same kind of plot, but this is when you get the recipe for how to make an axe. You don't actually get an axe, but you wake up one game and suddenly in the list of how to make things, you get an instruction recipe for how to make an axe. And you don't know what an axe is. You don't know if it's any good for anything, but maybe you try it. And if you try it, and even if you use it on all the trees properly after that, unfortunately, building the axe uses so many resources and takes up so much cost that you underperform compared to not using the axe. And so here, the game was being played normally without the axe. The axe recipe was presented to the agent. It tried it out, got a lower score, said that seems like a bad idea. And so for the rest of the trial, it ignored it and got back up to its normal performance. So the thing it learned is if you only have an axe recipe, ignore it. So what's novel in the research that I'm trying to describe in a moment? First of all, not the architecture. You're going to look at it and say, wow, I've seen many of those. What's new there? And the answer is it's not new. It's not intended to be new. What's new is some of the machinery inside the architecture itself. And I'll talk mostly about that. So our architecture is a fairly common planning and execution scheme. And yes, there's meta control to and goal reasoning as well. So you'll see how some of that works. And the planner itself is not novel. It's metric FF currently, but we've used other planners, and we would like to plug in a better planner if anybody's got one that can do a better job with cost optimization. And the adaptation approach in general is not entirely new. People have worked on adapting planning models and adapting goal sets for quite a while. But what we think is new is that we've developed a suite of domain-independent heuristics for model and goal adaptation that are very general. And in particular, their domain independence is being demonstrated by their use across these different programs, simulation domains in the Salon program. And then most importantly for Salon, we're doing single blind evaluation of the claim that this system is resilient to novelties, because the people who are developing the simulations do not reveal all their novelties to us. They give us a very small set to practice on. So for example, at the beginning in Polycraft, the only kind of new object we ever saw was an axe. So they gave us that example. They could probably introduce thousands of different kinds of objects that have different interactions with the world. And in evaluation, they do, but we don't get to see those. Our agent gets to see them, and we don't get to talk to the agent that saw them. So the evaluation is performed single blind and by the sim developers, not us. And we try and improve the performance of our agent kind of only by getting back, yeah, you got 7. Nice job. I'll show you some of the numbers we get back. So here's the architecture. I said it would look pretty familiar. In the gray box, we've got our domain simulations, and there has to be some kind of bridge to connect that symbolic representation of how do you represent Polycraft to how our architecture is meant to be domain independent and have its own representations of things. And we have a plan executive, which essentially just walks through a linear plan, executing it and watching to see if something weird happens in the world. And then we have our mission manager, which is where the really interesting stuff is. The mission manager has planning models that look fairly traditional and some novelty and hypothesis reasoning. And that's where our innovations come in. And I'll talk about those in a moment. And they have grounding methods, because some of the domain independent novelty and hypothesis reasoning needs to be grounded in a certain way in different domains. But the overall hypothesis is meant to be domain independent. And up here, we have this stock metric FF planner, so it's easy to plug in another one if we find one. So the big idea inside the mission manager is that the system can reason about hypotheses explicitly, and it does so when it receives unexpected observations. And the unexpected observations can be of several different types. The planner may fail to find a plan for some reason. So each time the system wakes up in a new game world, it synthesizes a model of, oh, this is where the trees are, and this is how the recipes I was given work for building a pogo stick. And it may not be able to even build a plan if there, for example, aren't enough recognizable resources in the world because of some change in how trees look or things like that. Also, during execution, plan aspects may fail, plan actions may fail. So for example, walking towards the tree when there's a fence block in your way, you don't understand whether fence blocks are actually something you can move through because they just have the word fence. But it turns out that the system doesn't get where it's supposed to go. And so that's a plan execution failure and would be an unexpected observation. Another kind of thing that can happen is that a new object appears that you've never heard of before, like an axe. You don't get any semantic knowledge about what an axe is. It doesn't say it's sharp and it's good at breaking trees. It's just a symbol, so it could be a foobar. So you have to figure out what to do with the foobar. And also, the system has to be built to be able to take new features. So for example, it may be the case that you've never seen colors before, but all of a sudden the novelty is that you can see colors on things, and that one's blue and that one's red, and maybe that makes a difference. And you should learn that. So the system gets all these different kinds of unexpected observations. And what it does in response is sort of in a holistic sense, try and manipulate its planning models and its goals in order to characterize what's going on and how it can take advantage of or avoid bad things in the world. And it does that by creating two kinds of hypotheses, generally speaking. One is a novelty hypothesis in the middle that's meant to give you a high-level holistic characterization of what a novelty is, like, hey, I understand there's now color in the world and blue is a good thing. And then from those holistic hypotheses, the system can generate testable hypotheses that it can run experiments in the world to see maybe that's right, maybe that's wrong. So it might try using blue axes to break trees and figure out whether blue axes are better than red axes and so on. And those hypotheses get back information in the form of, hey, now you can make a plan, or hey, I did run that operator that failed before, but using a new parameter, it worked. Or hey, that operator had a lower cost than usual. So once it gets those things, it can sort of validate its hypotheses and use them into future games. So I mentioned that the hypothesis space is really where we see some of our contributions. So I hope some of these sound a little bit interesting and very domain independent. Depending on what kind of unexpected observation the system gets, it can make one of these and a few other kinds of hypotheses. The first one that we've been talking about already is the preferred operator hypothesis. So the idea that breaking a block with an axe gives you lower action cost is captured into our PDDL planning models by specifying that if you have an axe, you should use it. And how do you prevent the other one from use no axe to break a block? How do you prevent that one from happening? Well, either by assigning it a higher action cost if you're using a cost optimizing planner, or just putting on a new precondition that says, use the axe if you have one, and only use the no axe action if you don't have an axe. And so that's actually how it works right now with metric FF. So there's a little PDDL, editing done on the fly automatically by the system. Another hypothesis that the system can create is actually a sort of hypothesis about game goals. And it should say a prefix game goal is a game goal that it should achieve before doing its normal thing. So for example, when you get the recipe to make an axe, maybe you should try making an axe before playing the rest of the game. And that's the example where, in fact, the system does create that hypothesis, tries it out, and actually invalidates it and rejects it and says, don't do that. And it will remember that rejection in a future game so that when it wakes up and gets the axe recipe, it'll say, no, don't use that recipe. And another kind of hypothesis system can make is that there are some bad arguments, one or more bad arguments being used in the parameters of an action. So for example, if you wake up in the polycraft world and all the blue blocks are suddenly indestructible, where normally they've been something you could break and use, then we would like to learn either that all the blue blocks are indestructible, or just that perhaps those particular blocks, like block 27, is indestructible and I should stop trying to break it. And that's where the bad arguments come in. So the system watches actions, and when it sees them fail, it might try them again, just in the hopes that there's something not really catastrophically wrong with the world, not really a big problem, just do it again. And maybe it takes 2 axe strokes to break a tree. But in fact, if you do it repeatedly, the system will eventually, and if the actions fail repeatedly, the system will construct the hypothesis that it's a bad argument to the operator and it won't use that argument set again. Another unique kind of domain independent representation hypothesis is that you have a misrepresentation. Something came in wrong in your percepts from the world, and you need to try to do something to those percepts in order to restore your functionality. So in Polycraft, that one form of that can take is that the recipe that you are given for how to build a pogo stick is actually wrong. It's been transformed somehow, or there's a ingredient substitution in it. And so you should play around with the recipe ingredients and the order that you put them together in order to try and figure out what was wrong with your perception of the recipe for pogo sticks. And as you kind of go down this list, we get into the hypotheses that the system has that require less knowledge and less specifics about even any of these domains. So when faced with fence blocks, rather than trying to actually construct an understanding of how geometry works and how navigation works through space, one thing that OpenMIND can do is respond with a novelty removal hypothesis. And the idea is that the system has detected novelty. It's seen these new blocks called fence blocks, but it has no idea what they are, and it can't understand why it can't seem to execute its plan. And so it can create the idea that hypothesis that maybe if I get rid of some of that novelty, my world will suddenly free up. And so it makes the hypothesis, maybe I can break some of those fence blocks, get them out of my world, and I can get to the trees and get on with the pogo stick making. And this is an example of what we're calling grounding methods. You can imagine that the novelty removal, make novelty go away, is kind of a very general idea. But in Polycraft, you need to ground it down to that domain operator that's breaking blocks. That's how you make things disappear in Polycraft. In Science Birds, the way you make things disappear is shooting them with birds. So there's these little grounding methods inside the reasoning engine that say, okay, I want to make novelty go away. How do I do it in this domain? And we had to have that little bit of domain specificity. The remove novelty hypotheses are actually also handled by another kind of behavior loop. It's not so much a hypothesis in of itself, but there's a behavior loop to handle repeated hypotheses. So you might want to break the novel blocks over and over. And you might want to break different amounts of them, different numbers of them in the domain. The system can detect, for example, that if there are hundreds of fence blocks and you try to play them all, you'll run out of time. The game has a time limit on it, and it knows that you won't get all those fence blocks broken before you try and get on with making pogo sticks. So it will try and break a smaller number of them and see if it can get to the trees. And then finally, our perhaps most obvious but last resort domain independent tactic for handling imperceptible novelty, when you don't see anything wrong, but you can't seem to make pogo sticks, for example, is to do anything. And a good example of where this is useful is in science birds, where, for example, we made up an ability for the system to not know it's a novelty, that the system as a whole was going to treat, let's say, ice blocks as pigs. So the game won't end because if you shoot all the pigs, there's still some ice blocks maybe. And the system is just waiting for you to do something. And OpenMIND has no idea why the game hasn't ended. There's no more pigs. I don't see anything novel. I've seen ice blocks, in many games before, but for some reason the game hasn't ended. So one thing you can do is just do anything and start shooting stuff, and maybe it'll shoot the ice blocks. Now you might say, well, doesn't that sound like the novelty removal hypothesis? And it's not quite the same thing, because in that case, you have to know that things are novel. The novelty knowledge helps you focus on what to do there. But in the last resort case of do anything, you don't have any perceptions of novelty except that the game hasn't ended. And so you're just going to do something. So those are some of the things that...
You have 3 minutes left. 3 minutes
Okay, thank
left.
you. Well, very quickly then, I'll try and sketch out how the evaluation works. And this is across the whole program. We submit our agents, they run them, and then they're looking at, among the metrics are these on change detection and performance. The first metric is the mean number of false negatives. So that's in the correctly detected trial. So if you detect that there's novelty in a trial and you're right about it, that's a CDT. And if you're late with your detection, you had some false negatives. After the red button was pushed, there's some false negatives. Another metric, M2, is the percentage of correctly detected trials amongst all the trials. And the other detection one is about looking at how many trials had a false positive, meaning you were wrong and those are not correctly detected trials. And performance is basically how does your after novelty adaptation agent work compared to the pre-novelty baseline agent. And so here's some numbers. They don't mean much to you, but I think there's a few that are interesting. For example, and this is after 18 months of working on Polycraft, for example, we were getting less than an average one false negative incorrectly directed child. So we're detecting the novelty on average in less than one game. So that's good. Some bad thing you might notice here is that in science birds, our percentage of correctly detected trials went down from the month 12 evaluation to month 18. And that was an interesting situation where we actually had a detector that was looking for novelty that was semi-randomly alerting. And it gave us a very high correctly detected percentage, but it was wrong most of the time. And so there were actually a lot of false positives. And so when we fixed that, we got a lot fewer false positives, but our correctly detected trial percentage went way down. And just to wrap up, I wanted to close with a few insights that I'll let you skim, but I think the really interesting one from the programmatic perspective is down at the bottom. It's very difficult to tell when you're doing a simulation, when you're doing a single blind evaluation like this, whether there's a bug in the simulation or the system has detected novelty. And because we don't get to see all the logs from everything that the simulation generators are doing for evaluation, we're never quite sure whether our system was performing well or performing badly, or there's actually a bug in the simulation. And both have occurred in the program already. And after the first big evaluation where this became apparent that this was a problem, a few extra novelties were revealed to us to help figure out whether there were bugs in the sim or bugs in our system. another fun insight is that it would be probably advantageous to add a little bit of stochastic behavior to our agent, because there are some forms of obstructive novelty, like in science birds, where if our agent always chooses this high trajectory shot at this pig and there's an indestructible block in the way, then it can't win. But if it every now and then takes the low shot, it'll do fine. And it doesn't have to detect or actually have a focused response. It just needs to be a little bit random, and it'll work beyond a bunch of kinds of novelty that are obstructive. And that's it for my time. Thank you.
Thank you, David. Excellent presentation and excellent timing. Appreciate both. So we have a few questions. The first one is from John Laird. He's asking the following. So there are some assumptions of locality that help avoid exhaustive search of the hypothesis space?
Basically, yes, and those assumptions are being challenged in the newest phase, where we're adding across the whole program, we're adding all sorts of new kinds of novelty. And so some of the new novelty, the space of hypotheses is enormous, even as we try and say, okay, let's keep it tamped down to things that are relevant and realistic. So this is a big challenge.
How can they make it possible for you to succeed? I mean, if you have all types of modifications to the physics of the world and to the objects of the world, then you can't search the hypothesis space in anything but exhaustive way, right?
Yeah, I mean, we're trying to use some of the observations to focus which kinds of novelty handling hypotheses we use.
Okay.
So there is some guidance there from the feedback that you get. Like if you get a new percept, then that's novel, then the expectation is that that's relevant. So
Yeah.
the Salon program has decided to mostly avoid irrelevant novelties. So they're not just sort of giving us all sorts of perceptions that don't matter. If they give us a novel perception, it's probably relevant, but we don't know whether it's a good thing or a bad thing. So we have to go and find out. But how to find out is very explosive. Yeah.
Great. Okay. Great talk. Thanks.
Thank you.
David, another question by David Aja. The question is, you seem to advocate a trade-off between exploration and exploitation in your final point. Would you consider modifying the trade-off over time, giving some feedback?
Modifying the trade-off of exploration versus over time. Yeah, so it basically does that already, in the sense that once it draws conclusions about hypotheses that it's explored and gotten some feedback, it doesn't re-explore them. So right now, after it tries out the bad recipe for the axe, I mean, it's a working recipe for the axe, but it's a negative impact on your overall performance. It will not revisit that novelty. And it basically, currently in the Salon program, we're only introducing one form of novelty and just assessing that one graph performance of the agent in response to that one novelty. So when we get into lifelong learning and more novelties arriving over time, that's going to be a new challenge. And I didn't put it up here, but we're just starting a new program under the Shell program, the Shared Experiences for Lifelong Learning, that's going to take OpenMIND and give it a communication ability and have it have the ability to learn knowledge with other agents in order to improve the performance of the overall team or system. And one of the things you can imagine then is that they can be doing a more or less coordinated search of the hypothesis space in parallel in order to be efficient and learn faster.
Thank you, David. One last quick question is low level. There are multiple heuristic planners. Is there any particular reason why you pick metric FF?
Well, we needed a planner that could do PDDL 2.1 because we need to keep track of how many blocks of wood we have and how many other ingredients that go into the pogo stick, for example. And we wanted to use a process-based PDDL, but the planning systems are really less scalable. And so some of these problems are quite large. When we get into Polycraft with dozens or hundreds of fence blocks, it really causes a lot of planners to just choke and fall over. And so right now, metric FF is one of the, we didn't do an intense evaluation across all the available planners. We just like, we need a planner now. Okay, here, Metric FF can do this. And so far it's scaling very well for the kinds of problems we've been using it for. Now these plans, some of them now, when we're playing Polycraft in the newer versions, the plans are fairly complex and leading to 25, 30 kinds of actions in the plan. So no, I mean, we'd be happy to have a better planner that actually could do process representations. We'll be digging around on that in the coming 6 months.
Thank you very much, David.